Hello, welcome back. We're going to start our next chapter over hypothesis testing. So here we're looking at an example of aluminum ingots, which are basically aluminum, which is melted down and then poured into these molds. These molds can be very, very large, up to like 20,000 pounds each individual block. And as they cool, it has to be in a very controlled environment. So as it cools, if one part of it cools faster than the other part, then it won't be uniform in its molecular structure or whatever, and it'll actually cause differences between strengths, and it won't be uniform, and so you'll start to have different fractures and different issues like that. If any speck of dust lands in it, that would also cause a defect, and it wouldn't be uniform like they need it to be. And again, we would have some defects that would show up after they take the aluminum block and they manufacture something from it. So there are certain aluminum blocks that a company manufactures out of 7075 aluminum, and they have these massive blocks that they use for aircraft. So they'll end up cutting them down and then using them to manufacture different parts for the aircraft. And so this individual ingot is 171 cubic feet, so it's absolutely massive. And then weighs about 30,000 pounds, so it's absolutely huge. Each one that they make, they test it with non-destructive testing, like ultrasound, believe it or not, just like what they do with airplanes. And if they have any defects in it or any cracks, they have to remelt it all back down and then do the whole process over again, which is very expensive. So last year, this company that manufactures these ingots, 20% of them had to be redone. They had some sort of defect in them, and so they were rejected, their quality control, and they had to be redone. This year, so far they've done 400 ingots, and of those 400, they had 68 of them that were defective. So if we do a percentage, 68 out of 400 is going to be 17%. So far it looks like there's a lower percentage this year than there was last year. So let's say that the company, after last year, after 20% had to be redone, they invested in some newer technology or new processes to try to reduce the amount or the proportion that was defective. So hopefully the changes paid off, and so far this year it looks like it's 17%, so it looks like it might be lower. But the next question we have is, if the 20% was what it was last year, well, out of the 400 that we've done so far, is this 17%, could that have occurred? Is that statistically significant, right? Is that an unusual observation, or could it have occurred by simple sampling variation? And so that's actually a question that we can answer. We can even quantify the probability of that occurring. So if the probability is still 20%, if it's going to be 20% this year, just like it was last year, then what's the probability that so far we would have observed 17%? Would that be unusual enough for us to be able to reject a null hypothesis, which we'll be doing today, in favor of an alternative hypothesis, which would be saying that the true proportion has decreased? All right, so the question we have to ask ourselves is 17% a statistically significant observation? Or in other words, is it unlikely to have occurred by chance? So if it did occur by chance, then our sampling distribution model would be centered at the 20%. So if there's still a 20% probability that any individual ingot would be defective, then the sampling distribution model would be a sampling distribution model with a sample size of 400, and the standard deviation, now it's no longer standard error because it's not based on a sample, it's based on the based on the hypothesized proportion, which would be for us 20%. We're going to assume that it's still 20% until we have enough evidence to suggest that it's now lower than 20%. So if it was 20%, then our P naught and our Q naught is going to be 20% and 80%. Now, the knots are basically a 0, and the reason we're using naught is because it's a hypothesized value or a null hypothesis. So it's going to be assuming that there's no difference or no change until we have enough evidence to suggest that there is a difference or there is a change. Then our sample size, of course, is 400. Whenever we put this in the calculator and take the square root, we get a standard deviation for our sampling distribution model of 2%. So it's centered at 20% with a standard deviation 2%. So I can fill in all these values. And if I go over to the 17%, which is where our observation was, out of the 400, we had 17%. The probability of that occurring, I can put it in the calculator just doing the normal CDF. So I go to second, distribution, normal CDF. I'm going from, I'm dealing with proportions. So my lowest proportion I could have would be 0. all the way up to 0.17 with a mean of 0.2 and a standard deviation of 0.02. All right, so the probability of that occurring would be 6.7%. So it's in the top 6.7% of unusual observations. So what we would end up doing, if we're going all the way to 17%, is we want to know what percentile rank is it. So we go from that 17% to anything worse or further away from 0 in this case, which would be 6.7% of the time. All right, so the question we have to ask, is that unusual? Well, it's not beyond 2 standard deviations. So if we're using our previous definition of what was unusual, no, because it was within 2 standard deviations, so it's not unusual. Now, it is fairly rare because this would only have occurred 6.7% of the time. So is that unusual enough for you? Well, that's when we have to get into setting an alpha level. So what we just did is a hypothesis test, and people want to answer questions like these all the time. So they might ask questions, has the president's approval rating changed since the last month? So we knew what his approval rating was last month. We sent out a sample or something like that, and a poll is that, and then it looks like it's gone down or it looks like it's gone up, but is it far enough away, or is it within the margin of error for us to not be able to conclude that it has changed or something like that? Has the teenage smoking decreased in the past 5 years? Well, we knew what the rates were 5 years ago. We know what we're at right now, at least so far. Is it enough evidence? Is it far enough away for our sample size for us to conclude that it's changed? Has it gone up? Has it gone down? Or is it just different? What are we interested in? Is the global temperature increasing, or did the Super Bowl ad we bought actually increase the sales? So we knew what our sales were last year, and then we know what we're selling so far this year, and then we make predictions of whether or not we believe, at least from what we've seen so far, if we're actually going to have enough sales that are different, and is it different a big enough of an increase that we would have justified buying those ads. So to answer questions like these, we test hypothesis about models. So that's hypothesis testing, which is really, really powerful stuff. So we have 2 hypotheses. We have the null hypothesis, which we denote H naught. Naught, again, like 0 means null or no difference, in other words. And then HA, which is the alternative hypothesis. So if we have enough evidence to reject the null hypothesis, then we would go instead with the alternative hypothesis. Now, in this case, our null hypothesis is that there's no change, which would mean that the true proportion is still 20%, because that's what it used to be. So we're going to assume there's no difference until we have enough evidence to say that there is. Now, in this case, there are 3 different alternative hypotheses you could choose from. You could say that the proportion is less than 20%, or that it's more than 20%, or that it is just different. So in this case, because we spent money, we're obviously trying to decrease our defect rate, and so we're really only interested not if it's increased, but only if it's decreased. So the correct one that we will be using for this one would actually be that the proportion has decreased. So we want to know, has it gone down? Okay. If it's gone up, then we would be looking at the right tail. So that would be something unusual, would be more than 2 standard deviations. So if we had a proportion at this point out of 400 of more than 24%, then we would say that we have enough evidence to say that it's gone up. If we have less than 16%, then within 2 standard deviations, what we used to be doing, then we would say we have enough evidence to say that it has gone down. The other way you could do it is a 2-tailed test, which is just to say, has it changed? Has it gone up or gone down? So sometimes that's what we're interested in. It doesn't matter if it's strictly less than or strictly greater than, then we would just say, is it different? Is it no longer 20%? Then we'll be doing a 2-tailed test, which goes from both sides. We'll talk more about 1-tail and 2-tailed tests tomorrow. All right, so next thing we have to do is choose an alpha level. So an alpha level is going to be also known as a significance level. So typical significance levels we use are 1%, 5%, and 10%. Now the default for us will typically be 5%. So if it just depends on how severe of what we're talking about. Like if we're talking about stuff that's not as important, like for instance candy or something like that, you'll get the reference later, but then it's okay if we set a fairly sloppy alpha level of 10%. But if we're talking about something that's very important, like life and death, like we will in the next example, then we're going to set the alpha level to something more strict, a stricter burden of proof, such as 1%. So setting the alpha level to the top 1%, the top 5%, or the top 10 percentile is setting the type 1 error. Those are exactly the same. And a type 1 error is a chance that we reject reject a true null hypothesis. So if our true hypothesis is actually it's still 20%, then 10% of the time, if we got a value here over 10% of the time, that could just be by random sampling variation. 5% of the time from here to the left, and 1% of the time from here to the left. So what percent of the time are you okay with being wrong? So you concluded that the hypothesis had actually gone down, or you concluded that the proportion had gone down when it actually hadn't. So that's what we call a type 1 error. So what percent of the time are you okay with being wrong and by committing a type 1 error? All right, so a good example of this burden of proof for alpha level is using the judicial system. So in our judicial system, so let's look at O.J. Simpson for an example. So there are two different courts with two different burden of proofs. I'm pretty sure I've talked about this with at least one of the classes before, but I don't remember if it was the A track or the B track, or if it was 6th hour or 2nd hour. I don't even remember, so I'm just going to have to say it all again. So O.J. Simpson, he did some things, you know, murdered his girlfriend, and then he wrote a book about it, If I Did It, and got away with it. Okay, so he was considered guilty or found liable in civil court, but in criminal court, he was not considered not guilty. So they didn't have enough evidence to convict him for that. So he didn't do any jail time, but he did lose a lot of money in the civil court. So the difference between the civil court and the criminal court is civil court is just talking about money. And so the burden of proof is a preponderance of evidence. So on a scale of not guilty, like pure as the driven snow, to you know, completely guilty, like this devil over here. So on the scale from not guilty to guilty over here, if it's more than a 50% chance or a preponderance of evidence, meaning it's more likely that you did it than you didn't do it, then we would find you guilty in a civil court and you'd be fiscally liable for the damages caused or whatever they're suing you for. But when it comes to criminal court, because now we're talking about jail time, maybe 25 to life, and we're talking about death sentence or something like that, we have a higher burden of proof, and it's beyond a reasonable doubt. So if a prudent and pertinent person or whatever, I don't know all legal stuff, I used to know it, right? But it's been a while since I've watched Law and Order. Anyway, if a reasonable person would have any, if a jury of 12, right, would have any reasonable doubt that you actually did it, if there's anything that the defense attorney could actually, any seed they could plant that would make anybody second guess or give you a reasonable doubt that you might not have done it, then we can't convict you for it and you go free. And so the burden of proof is like the top 99 percentile. So it's like there's a 1% chance that we might commit a type 1 error. But a type 1 error in this context is that, I mean, we're presuming you're innocent until proven guilty. So a type 1 error is that we rejected the null hypothesis. We said you were guilty when you actually weren't guilty. And the reason we have such a high burden of proof, not when it just comes to money in the civil court, because you can always earn money back, it's not the end of the world, but taking your life away, putting you in jail, separating you from your family and stuff, is that it freaks us out, the thought of putting an innocent person away in jail. And so that's why we set the burden of proof to be really high. So take this back to what we were talking about before. The burden of proof that we set, whether it's going to be 10% of the time that we're wrong and an innocent person goes to jail, 5% or 1%. So think about that. What percent of the time of all the people that we try that are, you know, the district attorney is you know, going to prosecute, of all the people criminals we prosecute, or what percent of them is it okay that we get it wrong, right? That we put them in jail. And if you think about it, I mean, clearly 10% is way too sloppy, right? 5%, which is our default. I don't want 5% of people, you know, to ruin their life by putting them in jail if they were innocent. Like the stars align, it just looks, or they got framed or something like that. They make movies about this stuff. It's scary. Even 1% of the time, I mean, that's pretty, I mean, to me, that still seems unacceptable, right? But at some point, we can't have the burden of proof to be so high that, like, we had to have several witnesses observe them in the act with the smoking gun and et cetera, and DNA and all this stuff. So we have to have some leeway, otherwise we wouldn't have a powerful enough system to be able to prosecute people and put guilty, dangerous people in jail, but we don't want it to be sloppy enough or insensitive enough that we actually put innocent people in jail. So that's really the question we're asking. So are we okay with being wrong 10% of the time, 5%, or 1% of the time with a type 1 error of basically putting an innocent person in jail? So hopefully helps you understand. So what do we do with a high p-value? So with our example, we went up to 17%, and so we had an observation of 17%, which gave us a p-value of 6.7%. Now the p-value is calculated off of the assumption that the null hypothesis is true. So if the null is true, if it's still 20%, then the probability of having a observation of 17% that we did out of 400 at that time would be in the top 6.7 percentile. Now that 6.7% is larger than our alpha value of 5%, so we would fail to reject the null hypothesis, and we would have to conclude that it actually hasn't changed and that it's likely that it's still going to be 20%, or at least we don't have enough evidence to reject that. Now if we would have chosen an alpha level of 10%, then because the alpha level, or our p-value, is less than the alpha level of 10%, saying that we did change that to an alpha level of 10%, then we would have been able to have enough evidence, because the alpha levels was rarer than the 10% burden of proof that we needed, so we were able to reject the null hypothesis in favor of the alternative hypothesis, and therefore we would say that like they were guilty, or we would say that we believe the true proportion of ingots that we're going to have this year that are defective is less than 20%, which means that our revisions that we did were successful. All right, so once we have said that we have enough evidence to reject the null hypothesis, the next thing that we would want to do, logically, would be to find the confidence interval for what we think that improvement is. So from the sample portion being the 20%, as soon as we get past that 10%, or the 5%, or the 1%, whatever our burden of proof is going to be, let's say it was 5%, we get here. So let's say we set an alpha level 10%, because it's not like life or death, not super important. It's just, do we think that there is enough evidence to suggest there's probably going to be an improvement? So let's say we use an alpha level of 10%. So we have enough evidence because it was a p-value of 6.7%, so it was in the top 10%, rare enough. So we believe that it has gone down. Then the next question is, how far has it gone down? So then from basing it on our sample proportion, which was 17%, we go out 90% in both directions, which would give us a certain margin of error, a critical value of 1.65 times whatever our standard error is going to be, which is probably going to be the 2%. It's going to change a little bit because now we're using 0.17 instead of 0.2, by the way. But more or less give us a confidence interval from, we believe the true proportion of defective ingots we're going to have this year is going to be anywhere from 13.7% to 20.3%. Now if you notice with this 20.3%, 20% is still included in that, and that's because if we're using a 90% confidence interval, what percent is on is going to be on one side of that tail? Well, if 90% is in the middle, it means 5% is on both sides, right? So the reason that 20% is still contained in here is because we use a 10% alpha level here, but if we would have used a 5% alpha level, then we would have failed to reject the null hypothesis. Okay, but we'll talk about testing hypothesis with confidence intervals in 2 days. So just hang on to that thought. All right, so what is a hypothesis test? A company makes a claim that such as a 2019 Toyota Camry gets 28 miles to the gallon. We go out and test our claim by testing the fuel economy of a random sample. We compare the results to the sampling distribution model of the sample size to decide if we have enough evidence to reject the claim or if we fail to reject the claim. So we start out with our null hypothesis, which is that it actually is the claim 28 miles to the gallon. And then once we have a large enough sample, that would give us, and we notice that it's different, whether it's greater than or less than, really we'd be interested probably in that one. An alternative that it was less than 28, that would be when we would be affected by it. Then once we have enough evidence or a small enough p-value, we'd be able to reject that claim or fail to reject the claim. So a null hypothesis is going to be that there's the claim being assessed of the hypothesis test is called null hypothesis. Usually the null hypothesis statement, if there's no change from the traditional value, no effect or no difference or no relationship, that's what the null part is all about. For a claim to be testable, null hypothesis must specify a value for some population parameter that can form the basis of assumption and sampling distribution for the test statistics. So sounds like a bunch of mumbo jumbo, but it just says we have to be able to use sampling distribution models and z-scores to be able to test this stuff. Alternative hypothesis would be proposing that we conclude what we should conclude if we find the null hypothesis to be unlikely. So that would be either that it is increased, or it's decreased, or it is changed in general. So an example of this would be hypothesis testing with fertilizer. So we're going to assume that there's no difference until we have enough evidence to suggest that there is enough change in the growth of the plants that the fertilizer must be helping. So it's kind of like innocent till proven guilty. We're going to assume that the fertilizer has no effect until we see a big enough difference from the control group that we have to conclude that it could not have occurred by chance. There's definitely something going on here, and the fertilizer does increase it. The p-value is the probability of observing a value or a test statistic that's at least as far from the hypothesized value as the statistic value actually observed if the null was true. So it's based on the assumption, the condition, that the null hypothesis is true. All right, so if it was really 20%, what's the probability of having a test statistic that we did of 17%? Well, that was, the p-value was 6.7%. Okay, so the 6.7% would be here. Now, there's a gradual scale that we have here from not significant to highly significant. So do we have no evidence, weak evidence, strong evidence, or overwhelming evidence? All right, so, and that's kind of corresponding with the p-value of 0, which would be very rare, like it's impossible that would happen, 1%, 5%, and 10%. So it's just kind of subjective in a way as we go here. So it just depends. Before we start out, we would always set our alpha level at either 1%, 5%, or 10%, depending on how important it is or how critical it is that we don't get it wrong and we don't have a type 1 error. All right, example 1. So we'll get started here. I'm going to try to go through this quick so we don't go too long. All right, write the null and alternative hypothesis you would use to test each situation. So part A says we field test a new flavor of soft drink, planning to market it only if we're sure that over 60% of the people like the flavor. All right, so our null hypothesis would be that it is exactly 60%, that the true proportion is exactly 60%. And then we, which would be, in other words, you can write it kind of with variables or write it in a sentence, okay? So P is equal to 60%, or that 60% of people like the flavor. Now that's not enough. We need to show that there's evidence that more than 60% does. So then our alternative would be that P is greater than 60%, or that more than 60% of the people like the flavor. So we're going to assume it's 60%, or assume innocent till proven guilty, right? We're going to assume there's only 60% of people like it until we have enough evidence to suggest that more than 60% of people like it, which would be our alternative hypothesis. All right, part B, 20% of cars on a certain model have needed costly transmission work after being driven between 50 and 100,000 miles. The manufacturer hopes that the redesign of transmission component has solved this problem. All right, so we're going to assume that it hasn't solved the problem until we have evidence that it has solved it. So if it was 20%, we're going to assume that it is still 20%, which is that 20% of cars still have defective transmissions. Now we're interested in hoping that it has decreased, so that it's less than 20% after the redesign, right? So we're only interested if the p-value has, or sorry, if the proportion has gone down, or there is less than 20%. So less than 20% of the redesigned cars have defective transmissions. Part C. In 1950s, only about 40% of high school graduates went to college. Has the percentage changed? So we're going to assume that it has not changed, and that the true proportion of teens that graduate and go on to college, or high school graduates that go on to college, is still 40%. Then we want to know if it's changed. So if it's changed, doesn't mean that it's gone down or that it's gone up. It could be either one. So this is where we're going to be a two-sided test, because we're just interested in knowing if it's no longer 40%. It doesn't matter if it's gone up or down. We just want to know if it's different. So we're going to say that now the P is not equal to, the true proportion is not equal to 40%, which means that the percent of high school grads that go to college is no longer 40%. 4. The seller of a loaded dice claims that it will favor the outcome of 6. We don't believe his claim, so we roll the dice 200 times to test the appropriate an appropriate hypothesis. So write the null and the alternative hypothesis. So we're going to assume that it is a fair dice until we have enough evidence to suggest that it is actually going to favor 6, so that's a loaded dice. So our null hypothesis is that the proportion is actually going to be that the dice is fair, so the proportion would be 1 out of 6 of those, okay? The alternative is that the dice is not fair, which means that the probability of rolling a 6 would actually be higher than 1 out of 6. So that it's not fair, that's loaded. Our p-value turns out to be 3%. So which conclusion is appropriate? So a p-value again is calculated based on the assumption that the null hypothesis was true. So if the dice was fair, the probability of us getting the number of 6s out of 200 that we did was only 3% of the time, which is pretty unusual, right? And then what we would do if we would reject our null hypothesis or fail to reject the null hypothesis would have to do with what we set our alpha level to. Is our alpha level 5%, 1%, or 10%? Now typically we default to 5%. This isn't like super serious life or death, so we're not going to do 1%. And I suppose just depending on how often it's okay for you to be wrong, you might be able to set the alpha level down to 10%. But even if we set it to 10% or 5%, it's still going to be statistically significant because our p-value was less than the alpha level with this 3% p-value. So our conclusion would be that we would have enough evidence to reject the null hypothesis that the dice was fair and to reject the null hypothesis in favor of the alternative that the dice is actually loaded, and it really does favor the outcome of 6. So does that mean which one is an appropriate conclusion or an appropriate interpretation of the p-value? Does that mean that there's a 3% chance that the dice is fair? No. Does that mean that there's a 97% chance the dice is fair? No, that's not what that means. There's a 3% chance that a loaded dice would randomly produce the results we observed. If so, it's reasonable to conclude the dice is fair. All right, so this is close, but it's actually flipped. So p-values are calculated from the sampling distribution model that assumes the null hypothesis is true, not that assuming that the alternative is true. So they just did it backwards. So the correct answer is actually be D. There's a 3% chance that a fair dice could randomly produce the results we observe. Since it's in the top 3%, which is beyond the alpha level of significance or the burden of proof that we have to have of 5% or even 10%, then we'd have enough evidence to reject the null hypothesis in favor of the alternative. So our correct answer for this one, the correct interpretation of a p-value of 3% is D. All right, last one I'm going to do with you is number 8, candy. Someone hands you a box of a dozen chocolate-covered candies, telling you that half are vanilla and the other half are peanut butter. You pick candies at random and discover the first 3 you eat are all vanilla. All right, if there really are 6 vanilla and 6 peanut butter candies in the box, what's the probability you would have picked 3 vanilla in a row? So on this one, we're basically doing the same stuff we learned back in the probability unit. So if you do alpha x, you can put it all in as a fraction, and we're going to do 6 times 5 times 4 because we're sampling without replacement. So there were 6 vanilla out of 12 at the first, then the second one would be 5 out of 11, and then the last one would be 4 out of 10, which altogether would be 1 out of 11. And I want to convert this to a decimal, so I'm going to go to math and then decimal, and it'll convert it. So basically 9%. All right, so what we just did is we just calculated p-value. So if the null hypothesis is true, if there really were 6 vanilla and 6 peanut butter, then the probability of observing what we just observed, 3 vanilla in a row, would be 9%. Now, is that unusual? Well, it depends on what you set your alpha level to. What percent of the time, what burden of proof, or what would be statistically significant in this case? Are you okay with being wrong 10% of the time and calling BS on your friend? Or whoever this person is? If that's okay, then you can set a sloppier alpha level of 10%. This certainly isn't life or death, so there's no reason to have a really high burden of proof, like beyond a reasonable doubt, of like 1%. So we probably would just default to 5%. Now, if we set an alpha level of 5%, then 9%, even though it's unusual, it would not be rare enough for us to be able to conclude that to call BS, right? And to be able to conclude that there really are not 6 vanilla and 6 peanut butter. So our p-value in this case would be 9%. So do you think that there really might have been 6 of each? Well, if the null hypothesis, which is that there were 6 vanilla and 6 peanut butter, is true, then the probability of having 3 vanilla in a row would be 9%. So that would be about right here. Now, that is rare, and if we set an alpha level 10%, yeah, that would be enough evidence to suggest that there's not actually 6 vanilla and 6 peanut butter. But if we set an alpha level of 5%, then no, that would not be unusual enough because our p-value is greater than our burden of proof of 5%. We need to be in the top 5%, but we were only in the top 9%, 9.1%. Would you continue to believe that half of them are vanilla if the fourth one you try is also vanilla? Okay, so then we would add an additional fourth one here. So if I go back up to my thing here, then I multiply that by 9, and on the top times 3, and then I'm going to take that fraction and convert it to a decimal. So go to math, decimal. All right, so now we're in the top 3%. Okay, so top 3% would be statistically significant even if we set an alpha level of 5%, which is what our default is. So yes, that would be unusual. So if I had 4 vanilla in a row, I would have enough evidence to call BS and say, okay, there's no way that there's 6 vanilla and 6 peanut butter. And if you really want to know for sure, then just try 3 more after that, and then if you if you get 7 vanilla, then you know it couldn't be true. All right, whatever. But at some point, we would actually have enough evidence to do that. And by the way, what we were doing would have been, it's not really even a binomial model because this is not Bernoulli trials, right? Because it's not independent. It's changing after each one. And we're sampling more than 10% because if we have 12, we can only sample 1 without violating the 10% condition. So you can still calculate the p-values and it still works, but it's not actually a normal model. Just something to think about. It's kind of cool. So if the null hypothesis is true, then the probability of having 4 in a row that are vanilla would be 3%, which would be unusual. All right, so that's all that I'm going to go through together with you. Sorry the video goes a little long. Every time we do a new chapter, there's a lot of new stuff and vocab here. I recommend reading the pages in the book if you're struggling with this, because we are really going to be doing hypothesis tests for the rest of the year, and it's really important. So if you didn't understand where we were going on here, read the 5 pages or whatever. It's on the top part of your assignment. So read those in the book and make sure that you're understanding and starting to wrap your brain around what's going on here. So I'll see you guys later. Let me know if you have any questions, okay?